Polynomials are extremely important in numerical analysis because computers can only add, subtract, multiply, and divide. You may think that they can evaluate trig functions and exponentials and logs, but in fact, if you want to evaluate the log or trig function, it has to go and approximate it by a polynomial or a rational function. Polynomials it can actually evaluate directly because all they involve is add, subtract, multiply, and divide, also rational functions. In particular, we're going to use the Taylor series a lot in this course, so let's review a little from Calculus 2. The Taylor series for a arbitrary function f expanded around the point C, you recall, looks like this. F of c plus f prime of c times x minus c plus 1 over 2 f double prime at c x minus c squared and so forth. It's essentially an infinite degree polynomial. Each of these is a constant. It may not look like a constant, but the function is evaluated at constant c, so that's just a constant plus a constant times x minus c plus constant times x minus c squared, so forth. So it's infinite degree polynomial. Computers can't do an infinite number of calculations, of course, so we have to stop after a finite number of terms. If we stop after n terms, actually n plus 1 terms, we have a polynomial of degree n, and we call that the Taylor polynomial of degree n. And the error that we get by truncating the series off and ignoring all the terms from n plus 1 on is called E sub n. So the error after n terms, well, the error in the Taylor polynomial degree n, really n plus 1 terms, looks like this. Here's the first term we ignored plus dot dot dot. Now the Taylor polynomial of degree n, which is the first line here, ignoring the error on the second line, can be easily shown to be the polynomial of degree n which agrees with f and its first derivative and its second derivative out to the nth derivative at the point C. So it's an Tn is extremely good approximation to f close to C. It may be a bad approximation far away from C. In any case, the error is given by this. Now from Calculus 2, you may recall that Taylor's error formula says that you can actually get rid of all the dot dot dots and write the error exactly in a single term, which looks a lot like the first term we ignored. It's easy to remember because it almost looks like the first term that we ignored, but it's the n plus first derivative of f is not evaluated at c, but at some point psi between x and c. Of course, if we don't know where psi is, you might say, what good is this error estimate? Well, we can get an upper bound by taking the worst case. In other words, we normally look at this and say, knowing that psi is somewhere between x and c, what's the biggest in absolute value that this can be? And that will give us a bound on the error. We can see by looking at the error term that what I suggested earlier is true, that when x is close to c, the error is extremely small, because when x is close to c, we have a small number raised to a large power, and that's extremely small number. On the other hand, when x is far from c, this can be extremely large. So the Taylor polynomial of degree n is generally only a good approximation to f close to c. How close, of course, depends on how many terms we take and the function itself. Often in this course, we'll write the Taylor series like this, where we've abbreviated x minus c and called that h. So x is just c plus h. It's equal to f of c plus f prime of c times h plus etc. So this is another way of writing the Taylor series. And in fact, usually we'll use x instead of c, so you'll see the Taylor series often in this form: f of x plus h is equal to f of x plus f prime of x times h plus 1 over 2 f double prime at x h squared and so forth. Now let's look at a very familiar example, the function e to the x. We'll expand it in a Taylor polynomial around the point 0. and all the x minus c's just become x's, and f and all of its derivatives are just e to the x. And so when you plug in x equal to 0, you get 1 for all of them. So f and all of its derivatives at c are just 1. So the Taylor polynomial degree n simplifies to this familiar form. The error in the Taylor polynomial degree n looks like this. The n plus first derivative at some point between x and c, x and 0, and n plus first derivative, like all the other derivatives, is just e to the x, so that just becomes e to the psi. Now, let's try to figure out how many terms we need in the Taylor polynomial to be sure of getting a very accurate approximation to e to the x in the range minus 100 to 100. In that case, the error, we can get a bound on the error by saying the biggest x can be an absolute value is 100, and since x is between minus 100 and 100 and psi is between x and 0, it also has to be between minus 100 and 100. So the biggest e to the psi can be is when psi is 100. So we get a error bound of e to the 100 times 100 to the n plus 1 power over n plus 1 factorial. And if we take n to be 700, then we have the following error bound on x for all x between minus 100 and 100. And this error bound is extremely small. It's less than 10 to the minus 200th power. So 700 terms is more than sufficient to give an extremely good approximation to e to the x in the entire interval minus 100 to 100. So I've written a little MATLAB function exs which returns the Taylor polynomial of degree 700 approximation to e to the x. And let's test this out and see how accurate it is. According to the theory, the error should be beyond the 200th decimal place. The first 200 decimals points to the right of the decimal should be all accurate for any value of x between minus 100 and 100, according to Taylor remainder theorem. So let's test our function exs at 1. That gives e 2.7183. Let's print things out a long format. And we compare that with the MATLAB system function exp. It agrees out to the last decimal place. Let's try our function on 50 and compare that with the MATLAB system function, and it also agrees out to almost the last digit, minus 10. Compare that to the system function, and it's relatively accurate, but notice that it's only accurate to about 7 decimal places, and after that it's not close. So let's try minus 50 and compare that to the system function at minus 50. And they're nowhere close. The true value of e to the minus 50 is on the order of 10 to the minus 22, and my Taylor polynomial degree 700 is giving a value of the order of 10 to the 4th. In other words, it's off by 26 orders of magnitude. It's total garbage. And that despite the fact that we've shown that the error in the Taylor polynomial degree 700 for any value between minus 100 and 100 should be out beyond the 200th decimal place. So what's going on? Well, it must be round-off error, because the truncation error is essentially 0. In numerical analysis, we deal with two types of error. One is we call the truncation error, which in this case is the Taylor polynomial error That is the error which has nothing to do with the computer we're using. That is the error that would exist if we did all of our arithmetic exactly. On the other hand, the round-off error has everything to do with the computer that we're using. The round-off error will go away when we do exact arithmetic. The truncation error will stay when we do exact arithmetic. But why are we getting such terrible round-off error for negative values of x, and it's not a problem for positive values? Well, if we look at our Taylor polynomial, we can see what's going on when x is negative, or rather minus x is negative. We have an alternating series. The odd terms are negative, the even terms are positive. If we put all the even terms together and all the odd terms together, the even terms actually add up to a very large number. Let's say when x is 50, so we're trying to calculate t of minus 50, then the even terms actually add up to a very large number. In fact, you may recognize this is exactly the Taylor series for the hyperbolic cosine of x. The odd terms also add up to a very large number, and you may recognize that as the hyperbolic sine of x. So for example, when we try to calculate t sub n of minus 50, the even terms essentially add up to hyperbolic cosine of 50, which is on the order of 10 to the 22nd power. The odd terms add up to hyperbolic sine of 50, which is also on the order of 10 to the 22nd power, and in fact they're almost exactly equal. In fact, since e to the minus 50 is on the order of 10 to the minus 21, these two must agree out to about 42 or 43 decimal digits. You can see that they agree exactly to the number of digits we printed out, but they actually agree out to about 40 digits. They only differ in the 41st or 42nd digit, which is total garbage because we simply can't store that many digits on our computer. MATLAB uses double precision. That's about 15 digits. So the positive terms added together after about the 15th digit, it's totally unknown. It's garbage. So when we subtract the two, we get total garbage, and that's the source of the serious round-off error. And you'll find in numerical analysis that always the source of catastrophic round-off error is the subtraction of two nearly equal numbers, such as we see here. When you multiply two numbers together, doesn't matter the magnitudes or signs, you're not going to get serious round-off error. You'll get some error out in the last bit, but not catastrophic round-off. You divide numbers, you don't get serious round-off. You add numbers of the same sign, not a problem. It's only when you subtract nearly equal numbers that you get the catastrophic round-off error. Now, sometimes it's almost impossible to alleviate this problem, but sometimes it's very easy. In this case, what can we do to improve our results to get rid of the round-off error when x is negative? In this case, it's very easy to solve the problem when x is negative. We can just use the fact that e to the minus x is 1 over e to the x, and when we need to calculate, for example, e to the minus 50, we simply calculate e to the 50. There is no round-off error problem there because all of the terms are positive, and simply take 1 over it. And let's try that. So now I've modified our MATLAB function and called it exs2, and it simply takes the absolute value of x and calculates the Taylor polynomial degree 700 on that absolute value, and then if x is negative, it just inverts it. So very simple fix. Let's see what happens when we try it. So let's calculate exs2 of minus 50, and now it gives us a very accurate result.